but it is not enough. Which T norm this is a condition? I need to know the T norm. That is, if these operators, child, are conditionals, they should verify the modus ponens inequality by some T norm T0. You need to know. In this case, usually is W. In this case, it's just this. T0 is this. It's a T norm we are considering. In this case, usually is W. And in this case is fantastic. In this case, is any T norm is valid. As any T norm is valid, we will take the greatest one, the minimum. Imagine T0, A, TAB. This is a smaller, this is a small, this is a T norm, and TAB. This is a T norm, this is a small T. For any T norm, those ponens is verified. Which one I will choose? The biggest one. I will go as much as possible towards B, and I will take the minimum. It's the minimum to make the composition of the inference by Z. Okay. Then, what I need to define is, at each case, this one, this is one. At this case is the easier one, because this case has a very nice property, is that when I will represent the implication through an R implication, sure that the ordering allows me to have the two principles, no conditions with me. In this case, I need also this kind of relation. S and A, B, A, B. In this case, I have A, B is not equal 1. If I don't leave T, A, B equal 1. But TAB equal 1 for a T norm that is not Kasevich, this is exactly the same as A equal B equal 1. Hence, in this case, this is exactly the relation. Exactly the relation. What I should do in these cases? Well, to particularize, S can be maximum, or a T norm in the family of product, or a T norm in the family of Kasevich. And I can particularize all these cases, I can go particularizing, and the final result, you can believe me, the final result is a family of results in that case, the result is this relation is the set of objects of the type 0B and the objects of the type A1 for A and B in 0. This case is solved. In this case, in only one case, when n equal n, when this is in the form W, when the negation is strong, and when the T norm is minimum, In this case, the relation is exactly the other. In the other cases, what happens is that the relation is always common. CwV A1 with A not 0, 1 and B 0. Okay. What happens then? Look, in Mandani, Larsen is impossible. Impossible. As the relation is that, I should have mu prime or x equal 1 and mu prime or x equal 1. If this is 1, this is 0. Okay? Then in Mandani case, if in my algebra of fuzzy sets I represent conditionals by Mandani-Larsen conditional, I have no principles of non-potential exclusion. It's impossible. There is no any solution. I have no these principles. What happens if in my algebra of fuzzy sets I have another implication? I have the principles. What happens, for example, in this case? I have no principles because, look, mu prime x should be 0. And then mu prime x, prime x should be b, that is any value. Okay, since this is 0 and this is any value, this should be 1. Okay, and for that, mu prime should be on x a, and mu prime on x should be 1. Okay, since this is any value and this is 1, this should be 0. Then the only possibility is that. Then in these cases, I will have no principle of excluded mu. Why? Because the only mu that will verify the principle are those verifying the principle in the classical way of mu prime equals 0. It's the only possibility. Of course, if my theory is one of these, my algebra is one of these algebra I told you, in which the T norm is Vukasevich, the T norm is Vukasevich, and the negation is between the two negations, of course, but not because of the implication, because of the algebra. The only cases in which there is a verification by the implication is residuated in some cases of the conditional expressions. Some cases appearing on the conditions. Is clear that situation? Well, this last part is a little bit more complicated because imagine only as implications I should consider maximum product in the family of product dual, in the family of the dual, if the negation that does coincide with the negation in phi or not, then in the paper this is large. But the final situation is that when the relation is exactly the ordering, I have the principles. If the relation is not exactly the ordering, I have no principles. Which advance means that for what we know, we didn't know. Of course, it is an advance, because our whole result is that the principles only to hold in the cases of the algebras in which the T norm is in Vukasevich family, the T conorm is in Vukasevich family, and the negation is between the two negations. Now we have much more cases. Any algebra is representing the implication either by an R implication or by a special kind of Q implications, we will find the principles. And there is some progress in the prior knowledge